Now start with simple unit cell or primitive cell. See this figure A represents the atoms of some element, and if we construct a unit cell, it is like this. You can see in figure B. Here it represents the atom of an element take part in unit cell and how they are arranged. And in figure C, it represents the cubic unit cell with lattice points. See this one also. A primitive unit cell can be shown in three different ways. In this figure, each small sphere shown to be present at all the 8 corners actually represents the center of the particle or a sphere and not its actual size. At the corners only, you can see 1/8 atom present in the unit cell and remaining part of the atoms is shared with the surrounding unit cells. And they also contain 1/8 atom at the corners. Okay. See this in figure B, how much part of an element is present at the corners of unit cell. Okay. Now calculate number of atoms in unit cell. Contribution by 1 point present at the corners to the unit cell is 1 by 8. This 1 by 8 represents this corners. And next 1 by 8 represents that one atom is shared with 8 neighboring unit cell. That means 1 by 8. And next, contribution by points present at 8 corners to the unit cell is 8 into 1 by 8. This set represents 8 corners of the unit cell and contribution of atom at the corner is 1 by 8. So 8 into 1 by 8 is 1. Hence we can say that each unit cell has one particle or point. Or we can also say like this, simple unit cell has one particle or one point. Okay. Next, body centered cubic unit cell. See these three figures A, B, C. In figure A, you can see a number of atoms are there, and if we construct a unit cell here, this is like this. In figure B, you can see. Yeah, these are the corner atoms. Okay, these atoms shared with their neighbors, and here one more center atom is there. You can see a blue atom. That body center atom is not shared by any other unit cell. Okay, and in figure C, you can see these are the lattice points, and it's only unit cubic unit. A body center cubic unit cell. Okay, and we construct like this unit cell. Yes, center atom contribution to this unit cell is 1, and corner atom contribution to unit cell is 1 by 8. Hence, contribution by 8 points present at the corners is 8 into 1 by 8. This set represents 8 corners, and 1 by 8 represents the contribution of atom in to each corner. That one is 1. Next, contribution by the point present in the body of the cell is 1. This one. This atom is not shared by any other unit cell. So its contribution is 1. And the total number of points or particles present in the body center cubic cell is 2. Next, face centered unit cell. See these figures A, B, C. In figure A, you can see atoms are there of some element and it construct a unit cell. In this, we get a unit cell like this. In figure B, you can see here coronal atoms contribution is 1 by 8. Okay, and see here face of this unit cell is contain half of atom in this one and remaining half of atom is shared with its neighbor. See this here, this face also, this face. Total 6 faces are there and all these 6 faces share half of atom with their neighbors. In figure C, we can see here lattice points are there. These are the lattice points and this one represent the face centered unit cell. See this. Now calculate number of atoms present in FCC. Here top bottom half atom is there. Okay, in figure B you can see this one, top bottom left side and right side. Okay, half atom is there. And next front and back half atom, total 6 faces and all 6 faces contains half of the atom and coronal contribution is 1 by 8. So now calculate contribution by 8 points present at the corners is 8 into 1 by 8 is 1 and contribution by 6 points present on the center of 6 faces. This 6 represent the faces, 6 faces of the unit cell and each face contains half of the atom or half particle. So its value is 3. Therefore, total number of particles or points present in face centered unit cell is 4. Now come to next point, that is coordination number. First one, simple cubic. Let's take one crystal structure. Okay, here one unit cell is there. In this structure, we construct 8 unit cells. This one 1, 2, 3, 4 and below 5, 6 and here this side 7 and 8. Okay, here is unit cell of this structure. Now take this center atom as O. Now let's calculate how many number of atoms are nearest to this center atom. So this is first 1, 2, 3, 4, 5 top, 6 bottom. Total 6 atoms are nearest to this center atom. Okay. In this figure you can see only 3, 4 and 5 and remaining atoms 1, 2 and 6 are the nearest atoms of their surrounding unit cell. Okay. And if you see A, say this atom A and this atom B, this atom C and this one atom D, they are not the nearest atom to this center atom because they are diagonally arranged. And if you see this one A, B, 1, 2, 3, 4, 5, 6, they are present at equidistance. Okay, here A, B, C, D are the diagonally arranged, so they are not the nearest. Hence, this center atom has 6 nearest neighbors. Hence, its hence its coordination number is 6. And the example is polonium. Body centered cubic. See this unit cell. Now to calculate the coordination number in BCC, take this center atom as a origin. Okay, now calculate how many numbers or how many atoms are nearest to this one. Yeah, 1. Remember, this one is at the center of the body. Okay, all these. Okay, now calculate first one. 1, 2, 3, 4, 5, 6, 7 and 8. Remember, this one is a center atom, hence the 8 corners are equidistant to this one, and the nearest neighbor for this atom is 8. Therefore, the number of nearest body center atom is 8. Therefore, the coordination number of BCC is 8. An example for body-centered cubic is sodium, barium, uranium, etc. Now, face-centered cubic. To calculate coordination number in FCC, there is crystal structure 3 dimension, and for reference, take this one unit cell. Okay, and with respect to this unit cell, we have to calculate nearest neighbors. For this one, let's take one atom as origin O. Okay, in FCC structure, the nearest neighbor atom to the corner atom in the face centered atoms and not the corner atoms. For any corner atom, there are 8 unit cells surrounding it. Hence, each corner atom has 4 neighboring atoms in its own plane. That is 1, 2, 3, 4. 4 neighboring atoms in a plane above to this center atom. 5, 6, 7, 8 and 4 neighboring atoms in a plane below it. That is 9, 10, 11, 12. Here on its own plane 4 atoms, above plane 4 atoms, that is 5, 6, 7, 8, and below plane 4 atoms 9, 10, 11, 12. Hence the coordination number is 12. Examples are copper, silver, gold, etc. Now this is about how to calculate the number of atoms in simple cubic, body centered cubic and plane centered cubic. And next one was coordination number. Remember here, coordination number is the nearest neighboring atoms of each atom in a unit cell. Okay, and in next class we will discuss Bravas lattice in 2 dimension. Thank you.